In this video, we'll look at the second long question from section 2 of the 2017 exam.
In the first part, we see a graph of current against voltage and four different lines on this graph, and we're supposed to say which of these is a voltage characteristic of an 8 ohm resistor. So what are the features of a voltage characteristic of a resistor in general? Resistors have straight line voltage characteristics. The resistance is a constant of proportionality between voltage and current, so this should be a straight line, at least for a reasonable range of currents and voltages. Since only Y is a straight line, Y is the voltage characteristic of a resistor, and answer C was the correct one. Part B, on a similar note, which is the voltage characteristic of a filament lamp? Well, in order for the filament lamp to glow, the resistance must grow rapidly with current. This high resistance is what makes the lamp glow. The energy is not passed through the filament, but it's radiated as electromagnetic radiation. So we need to look for a voltage characteristic where R gets really big with high currents. And R is V over I. So V needs to grow rapidly with small changes of the current, and that's exactly what X does. In other words, the gradient is a small number, small positive number. So X is a lamp and B is the correct answer. Now the lamp and the resistor are connected to a 6-volt supply in parallel, and the power dissipated in the lamp is 9 watts, and the resistance of the resistor is 8 ohm. And we're supposed to say what the current flowing through the ammeter here will be. The power is voltage times current, and voltage by Ohm's law is resistance times current. And as you can see, from both of these, we can express the current. And we'll do exactly that. So for the lamp, the current is power divided by voltage, the first formula, and for the resistor, it's voltage divided by resistance. And using the numbers provided, we see that current through the lamp is 1.5 amps, while the current through the other branch, through the resistor, is 0.75 amps. Now, what happens to current in two parallel branches when they then reconnect? Well, by Kirchhoff's current laws, the amount of current flowing into this node must be the same as the amount of current flowing out. So we just simply add the two currents from the two branches to get the current in the main part of the circuit, and that's 2.25 amps, which was option D. In section D, two elements, W and Y, from the first section, once we saw in the graph, are now connected in a new circuit, this time in series. And we are supposed to consider these 5 statements and say which one of these is true about the setup. So let's look at the first one. W and Y dissipate equal power. When we say power, we should immediately think voltage and current, their product. So what happens in series is that the voltage is split between the two elements in the ratio of their resistances, and the current is the same through both. So the current is the same, but the voltages are different, and that means that the product of current and voltage is different for every one element, and they do not dissipate equal power. So how about B? W and Y have equal voltages across them. That's true in parallel. Two elements in parallel will always have the same voltage across them, different currents, but the same voltage. It's the opposite of what happens in series. But here we are in series, and as we said before, the voltages are different. So B is wrong. And C, finally, is the one which is correct. In series, equal currents flow through all elements. So we found our correct answer, C. And the other two statements, they're a bit more complicated. We'd actually probably have to do some calculations to justify that they're both wrong. But generally speaking, when we have a setup and we are comparing two elements on their own, in parallel and in series, then the setup in series is the most power demanding. Part E is about the same circuit again, where we have the resistor of 8 ohms and the unknown element W in series and a voltage 6 volts applied across these two elements. And the question is, how much power is dissipated by W? First of all, we notice that W is a diode. It has infinite resistance, then suddenly almost zero resistance. So let's look at it in more detail. So one thing we know for sure is that the voltage on the resistor
is the total voltage supplied minus the voltage of the diode by Kirchhoff's voltage law. And now let's try and express the current through the resistor in terms of the voltage on the diode. That will be the voltage on the resistor divided by the resistance, and this voltage on the resistor can in turn be expressed with our first formula as 6 minus Vd, and that's 6 minus Vd over 8 ohms. And this is an equation of a straight line with intercept 6 divided by 8 is 0.75 and a negative slope, just like this. So it starts at 0.775 and crosses the x-axis at voltage 6 volts. 6 minus 6 is 0. From the previous section we know that because the two elements are in series, there must be the same current flowing through them. And now that we have the two graphs, the red one being the current through the diode depending on the voltage on the diode, and the blue one current through the resistor depending on the voltage through the diode, we see that the two currents will be equal at their intersection. And that is approximately at current 0.5 amps and voltage 2 volts. Now that we have the current and the voltage through the diode at which it operates in this particular circuit, we can use the formula for power in terms of current and voltage. It's the product, 0.5 times 2 equals 1 watt. And that's option B, and our final answer.